Welcome back to CS 520. In this session I'm going to talk about converting 32-bit integers to IEEE single precision floating point. I'm going to do this by working an example. Okay, so I'm given these bits expressed in hex again, and I'm told that that's a 32-bit integer, and I want to convert that integer value to a IEEE single precision float value, and I want to know what the bits would look like after that conversion. So let's take a look at this case. Let's start out by just writing the bits down again. Okay, so that's the 32 bits and the integer value. In essence, again, I can think of that as being that number with a radix point right there times 2 to the 0. So my first job is to normalize the value. Again, normalization means I've got to shift right, right? I'm going to have to shift right in order to bring the radix point all the way over there. Okay, so how many bit positions is that? Well, I'm going to have to shift 4, 8, 12, 16, 20, 24, 28, 29 bit positions. So I'm going to end up with a value 2 to the 29th. Okay, and let's just write that out. It's the same value, I just moved the radix point over. Oops, I missed, didn't I? Let me rewrite this here. Okay. So let's just make sure I got that right. Got the 1, 1, and then the 0, 1, 0, 0, 0, 1, 0, 1. Yeah, I think I've got that right now. Okay, so now the value is normalized. However, it's not quite ready to be packed into an IEEE floating point value because an IEEE value only has room for 23 bits of the significand. The 1 bit to the left of the radix will not be stored, so we don't have to worry about that, but I'm only going to be able to pick up 23 bits. So 1, 2, 3, 4, 5, 9, 13, 17, 21, 22, 23. So I'm going to have to chop the number off there. Okay. The question is that all we do? Do we always just truncate? Well, it turns out in this case, yes, we just truncate. But in general, and I'll have another slide in a second to talk about this, these 2 bits here are called the guard bits. And the rest of the bits that are discarded are summarized as either 0 or 1. I give a summary of 0 if all these bits are 0 and this is 1 otherwise. Okay. And again, I'll state the rules on another slide, but right now in this case it's a 0, 1 here, and what that tells us in this case, we're just going to truncate. truncate extra bits. Again, if you think back to back to chemistry class, when maybe you first saw scientific notation, my chemistry teacher anyways had a rounding algorithm. You were only supposed to keep so many digits of accuracy, and you would round the last one. And in base 10, of course, if it was less than 5, you would truncate. If it's greater than 5, you would round up in that last position that you were saving. And if it was 5, then, there was various ways to do it. As we'll see, the hardware, in this case, the IEEE specification, has a setting called round to even, which says that if you are in the middle, then you will round the last bit, sometimes down, sometimes up. And we'll talk about that more in a minute. Let's go ahead and finish this example, however. What do I have to do now to pack this number into a IEEE single precision value? Well, first thing is I've got to figure out what the exponent is going to be. Again, if you remember, the formula is the actual exponent equals the stored exponent minus the bias amount, which for single precision is 127. So in this case, the actual exponent is 29. The stored exponent is unknown, so we're solving for that. So the stored exponent is going to be 156. Okay. What's 156? That's again base 10. We need to get that into binary, so it's 128 plus 28, so no 64, no 32, but I do have a 16, I do have an 8. Let's see, I've got to get back. I got 128, I've got 16 and 8 is 24, and I need a 4, I guess. No 2, no 1. Okay. At this point in time now, I can write down the final answer. Notice the number was positive. We could tell that by the leftmost bit of the original integer. So I'm going to have a sign of 0 on the floating point. Okay. The exponent we just saw is 1, 0, 0, 1, 1, 1, 0, 0. And the significand then I copy from up here, right? I copy these bits down into the significand. 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, and the 1, 0 on the end. Okay. If I've done this right, I should have 32 bits. Let's take a look. Divided into 4-bit chunks. 3, 4, 5, 6, 7, 8, in fact. And then looking at it in hex, the result is 4 E 5 1 5 9 E 2. Let me check my answer here, make sure I got the right answer. 4E5159E2. That is correct. Okay. So that illustrates what you have to do to convert ints to floats. If you're writing a C program, obviously you could capture the bits. You have the bits in an integer value. You can manipulate those bits in those integer values. figure out the exponent, come up with an exponent representation, a biased exponent representation, and put all the pieces back together again. Okay. All right, let's take a look at that roundings a little bit more closely. Again, what we're talking about here is one particular floating point rounding mode that IEEE supports, which seems to be what is commonly used. At least it's used on the Intel hardware. The rounding strategy is called round to even. It's based upon the guard bits and the sticky bit, which I illustrated in the last example. The guard bits are the two highest bits to be discarded. Okay, again, you can only keep 23 bits in the significand, so we're talking about the guard bits being bit 24 and 25. Okay. And then we also need to think about something that is called the sticky bit. The sticky bit summarizes all other discarded bits. If all other bits, in other words, bit positions 26 and higher, are all zeros, then sticky bit is 0. So if all other discarded bits, again, I guess I should be careful. I'm talking about bit position, but I didn't really mean that. Right, where I'm talking about looking at the, maybe I should draw a little picture up here. Right, you decide where the radix point goes in order to normalize, and then you've got bits hanging to the right here. Again, just think back to that earlier example. And I can only keep 23 bits. All right, so there's a boundary here, and these are bits 1 to 23 to the right of the radix point. The guard bits are the next two bits, and then the sticky bit summarizes everything else to the right here. Okay, so that's what I mean by the guard bits and the sticky bit. And the sticky bit summarizes all these other bits in here. If they're all zeros, then the sticky bit is 0. Otherwise, the sticky bit is set to 1. Okay, and then round to even means you look at the guard bits, and if the guard bits are 0 or 0 and 1, it doesn't really, the sticky bit doesn't really factor in then. You're just going to truncate those extra bits, the bits to the right of this dividing line here. Just going to throw them away and just store these bits as is into the floating point value. Similarly, if the guard bit is 1, 1, then we want to round up. We want to round up by add 1 here. Right? And again, if you think back to high school chemistry class, we have those two bits are clearly above 1/2, and so we're rounding up. And we round up by adding 1 to that last bit position that we're going to save. The tricky thing is in the middle here, and this is where round to even comes in. If I have a 1, 0 in the guard bits, a 1, 0 here, then that's exactly 1/2. Right? And I'm not sure what to do. Well, one case is I look at the guard bits, I looked at the sticky bit then. If the sticky bit is 1, that means there's some 1 bit out in here somewhere. So it is a little bit more than 1/2. It's a little bit more than 1/2 because there's a 1 bit out here somewhere. In that case then, I add 1. Again, I add 1 to that 23rd position there. Okay. So that brings us down to only one case, which is round to even. So in this case, again, I have the guard bits of 1, 0, and a sticky bit of 0, meaning all these other bits, everything else I know is 0. So it's exactly 1/2. In this case, we add 1, if the low bit is a 1, indicating the number is odd. So we're going to round up to an even number. And if the last bit here is a 0, we're going to leave it alone. Okay. Let me show you another slide to emphasize this. Right, there's basically 3 actions in that little table. Truncate, which means just discard the extra bits. Add 1, which means add 1 to the significand. Add 1 to the bottom bit position of the significand. Note that when you add 1, if all the bits in the significand are all 1s, you're going to get a ripple all the way across, and you could end up, so if you're in this situation, where you're the significand, you're rounding, it looks like that. Obviously one bit to the left of the radix, then all 1s to the right of the radix. When you add 1, and to round up, you're going to end up with 0s here. You're going to end up with this. Okay, that number is no longer normalized. Right, I've got a 0 and a 1 to the left of the radix. So you'd have to shift it back right, and adjust the exponent. So shift right, and adjust the exponent. So that's one special case you got to keep track of. All right, the middle case then is what I was looking at more carefully in the example. Round to even means if the low bit in the significand is a 1, add 1, else do nothing. So the idea is you're going to end up after rounding with an even number. In other words, with the rightmost bit being 0. Okay. So what you want to do is you want to go work some of these cases yourself. And let me suggest a few that you might want to look at. And these are all closely related to the one I worked up, obviously. I've just varied some of the bottom bits in order to illustrate some of the other cases. So in this case, I end up with the guard bits being 1, 0, and the sticky bit 0. So this is exactly that illustrates the case, round to even. But the low bit is already 0, also in this case. So the number's already even, so nothing is done in this case. And if you do it right, you should end up with the same answers we got on the example I worked. Because again, you're essentially just discarding the extra bits. Okay. This one will illustrate round to even, where you actually do need to add the 1. You end up with the guard bits of 1, 0, and sticky bit is 0. But the low bit will be a 1 this time. In other words, the number is odd, so I will go ahead and add 1 in order to get an even number after rounding. Okay, so you should work that and see how that works. Make sure you understand it. The other cases in that table would be a case where I have the guard bits of 1, 0 and a sticky bit 1, so I'm always adding 1 in this case, right? This is a little bit more than 1/2. We have exactly 1/2 of the guard bits, but we got some 1 bit out to the right somewhere, so it's more than 1/2, so I'm going to round up. In this case, I'll end up with a different answer. Okay, and finally, a case where I have the guard bits are 1, 1. And in this case, it doesn't matter what the sticky bit is. It's clearly a value greater than 1/2, so I want to round up that last bit position by adding 1 to it. Okay. In this case, I get a different answer. Okay. All right. I claim that's what you need to know in order to be able to implement conversion of integers to floating point. So think about that, work those examples, and please raise any questions that come up as you do that.